Welcome to another episode of the Arm Viewpoints podcast, where we explore technology topics at the intersection of AI and human imagination. I'm your host, Brian Fuller. Today, we're going to dive into one of the most exciting developments shaping the future of computing: how Arm and NVIDIA are working together to redefine the data center landscape. From the power of the Grace CPU and superchip architectures to the impact of accelerating computing on AI and high-performance workloads, this collaboration is transforming how we think about efficiency, performance, and scalability. Joining us are Ian Finder, Group Product Manager at NVIDIA, and Robbie Williamson, Senior Director of Engineering with Arm's infrastructure line of business. In this episode, we explore how Arm and NVIDIA are collaborating to drive the next generation of AI and high-performance computing, the unique advantages of the Grace CPU and Grace superchip in modern data centers, how Grace Hopper and Grace Blackwell superchips handle AI workloads from training to inference, why power efficiency and customization are critical in today's computing landscape, the evolving software ecosystem and how developers can easily migrate applications to ARM-based solutions, and why Robbie's Iron Man training is the perfect metaphor for these technologies. Let's dive right in. So, Ian, Robbie, welcome. Thanks for joining us today. How are you guys doing?
I'm doing great. It's Friday, so the weekend's coming up, and this is good for me.
Doing all right too. Can't complain. Thanks for having us on.
So, there's been a lot of buzz lately about how NVIDIA and Arm are reshaping the data center landscape together, particularly with Grace CPU and the various CPU architectures. So we want to do a little deep dive to better understand this collaboration. So let's start at a high level. Give us an overview, and I guess we'll start with Ian. Give us an overview of how Arm and NVIDIA are collaborating on next generation computing solutions and why the world should care.
Yeah, well, I think it's great to have a standards-driven ecosystem, which is what Arm is doing with things like Arm Server Ready, that allow us to innovate on the CPU. We can build all sorts of different things. We can innovate on microarchitecture if we choose to. We can innovate on I/O, on fabrics. We can choose where we want to add value, and that can be typically, like you'll see with Grace Hopper, in an accelerated compute ecosystem, right? Where we built a CPU around exceptional memory bandwidth per watt, exceptional memory bandwidth per dollar, AIDL workloads that need that kind of memory bandwidth and that kind of connectivity into the CPU fabric. And when we do all that, we have fundamentally a chip that can still run the same software as everyone else. And so we've moved into a world where we're free to innovate on microarchitecture, on I/O, on fabric, on needle movers, and we don't have to break the mold on things like software compatibility, driver compatibility. If someone takes a Docker container from AWS, they run it on Grace, it's going to work great. And that's a really, really powerful thing to be able to do, and something that historically, if you look to some of the great architectures of the past, that frankly the industry has struggled with, right? You look at things. I'm not going to pick on anyone in specific, but you can go back to the 80s and see this like rich ecosystem of really, really great varied CPU ideas that were totally incompatible with each other from a software ecosystem perspective. And now we don't have that friction. We can all build our best product for our best use case and share that ecosystem.
So Neoverse is a foundation for Grace CPU and the superchip architectures. What makes it particularly well suited for that? And I perhaps first, for the unfamiliar, could you describe the difference between Grace and the Grace superchip?
Yeah, so Grace refers to our first generation CPU product for the data center, and Grace superchip is a way that we package Grace. So Grace is the chip, Grace is the SoC, and when we have things like Grace superchip, that's effectively two Grace SoCs on a very, very fast socket-to-socket link or chip-to-chip link, put onto a module with the industry's first data center class deployment of LPDDR memory. That's a huge thing for us. And what Superchip gives you is it takes that Grace technology and it packages it into something that embodies the essence of, let's say, like a high-end two-socket x86-like server similar kinds of performance, similar kinds of memory bandwidth, and that super chip module, because of the design point we've used, because of the LPDDR memory, is actually, in many cases, 2x the performance per watt of competing parts. We're able to do that at a system level, right? Your SoC is only as good, if you build the most power efficient SoC in the world, and if the memory takes a bunch of power, you've only moved the needle this much. So Superchip was a way for us to get the technology of the memory, the packaging, the socket to socket link, the CPU into the market, without having to build a whole new, ecosystem of servers in one go. And I think what you'll see with other products we've announced, such as C1, is you're starting to see a more diverse set of form factors as the industry ecosystem gets on board with Grace. Things like single socket designs, chip down designs, right? That you're starting to see as well. So Superchip was a great go-to-market vehicle that allowed people to move quickly. There was a question on Neoverse in there as well. In the Neoverse IP, we found a core that was, pretty good data center class core. And for our use cases, as I mentioned, we like to pick where we innovate. There's all these different places we can innovate. That's the cool thing. We can do the microarchitecture, we can do the IO. With Grace, we chose to innovate on really the fabric. What we found is, for a lot of the workloads that we wanted to target, we wanted high bandwidth core-to-core communications for the types of things that don't necessarily move to GPU, right? Sparse, branchy, memory-intensive workloads, lots of fork joint concurrency. So we built a totally custom NVIDIA fabric that we call our scalable coherency fabric. It's about twice the bisection bandwidth of competing products. It's 72 cores on a single NUMA domain. There's no sub-NUMA islands. This is a really, really great fabric. And by using Neoverse, it allowed us to spend our design cycles on building that fabric, which is how Grace was able to get, partially how Grace was able to get the exceptional performance that it did.
Yep. Robbie, we have some questions for you later on, but feel free if you want to jump in here.
No, you're good. You're good. I have the same problem, so I totally understand. It just comes with the roles, right? But no, I think Neoverse, specifically the V series, right? It's like, the design, the mindset of ARM going into that design was, for high-end HPC level, big compute, right? And it was a perfect marriage for NVIDIA to go after the V series, IP, and then again to marry it with their expertise, in terms of, the mesh and obviously, the GPU, right? And I think the cool thing that happened was, yes, great. There are workloads that you absolutely need to transfer to GPU. We all know this, especially from the AI perspective. But, being able to take full advantage of just your general purpose compute workloads in the same system is where you get the benefit of the Neoverse, because it's the same line that we've kind of pounded through the cloud partners and really iterated on and learned from that, so that NVIDIA could take that IP and take advantage of what we've learned, right? I mean, I think that the thing that ARM brings to the table is that our partnerships, with all the hyperscalers, we've learned a lot. We could put that into the IP so that NVIDIA can actually produce, the highest powered ARM server you can buy off the shelf right now, de facto, right? So, and again, I think, just to reiterate on the point around, multi-architectures and, the 80s and 90s, having worked at previous companies that have done previous architectures and lived that pain of software. It's always the software, no matter how great the architecture is. If you don't have that ecosystem around it, if developers have to recompile, if it doesn't work, it doesn't take off. I don't care how great the hardware is, right? Now I'm a software guy, of course I said that, but at the same time, it's true. And I think the cool part is that, as you said, it's going to work. You could take, a binary, run it on AWS cloud. It's going to run on NVIDIA ARM. You don't have to do anything. It may run better. You could tweak it, but there's no recompile. There's a library mismatch. No, ARM is ARM now. And in the past, it really wasn't. And that was really painful, right? If you lived through the previous iterations of the ARM server adventure as we have.
Yeah.
One of the things I think people actually miss that you touched on, Robbie, is that, people always think about this at the application and kind of container level, which used to be, as you mentioned, kind of a Wild West that is now very, very easy story to tell. But I don't think people realize how deep down into the stack that compatibility has actually got. We're talking about if NVIDIA provides a driver for our ConnectX series NICs, on ARM, that driver will run on a Grace platform. It will run any other ARM platform. If we write, a PCI Express GPU driver, all the low-level systems code is
That's a very good point.
into the workloads, and
Yes.
that's huge.
Yes, because in another prior life, I was, in the distro world of Linux, and having to have separate kernels for different ARM variants of servers is not ideal. when the competition just had one, right? So it was like, exactly.
So, Robbie, you run Ironman triathlons, and when I think of the great CPU super chip, I think Ironman triathlon. Yes, it's more of a question for you, I guess. What kind of server workloads is the great CPU chip being optimized for these days?
Well, I think what you have to do is you have to look at the incredible growth in accelerated computing. I mean, for our customer base and for the kinds of workloads that people do on accelerated computing, AI, AI, ML, DL workloads, we continue to be able to get, frankly, like 2x year over year kinds of gains through employing a bunch of optimizations that we can do in the parallel compute world, things like mixed precision, things like sparsity. And we're able to drive incredible progress gen on gen in GPU performance. And when you do that, there's these other workloads that people are doing near their GPUs, things like ETL, like graph analytics, vector databases, right? There's this entire world of structured data that doesn't always get the benefit of those immense parallel compute optimizations that go into the GPU. And what our goal is really to build a CPU that's for an AI-focused, AI-centric world. And so it's great at things like, breadth-first search algorithms love our fabric. They fan out, they fan down, they fan up, they fan down. You can get something like, literally 2x the performance per socket versus some of the best competition out there with those types of workloads. Same with things like ETL on structured data. And there's a very, very conscious thing, because in kind of an unaccelerated lens on structured data, these are the workloads that are going alongside large GPU deployments. But you can actually take it a step further, and you can think about the potential now with, again, being able to have a standard CPU architecture, but being able to have shared memory with the GPU, coherent memory with the GPU, extremely high bandwidth to the GPU, relatively low latency to the GPU. You can also start to see how the line between what a CPU workload and GPU workload is can become blurred a little bit, because now, you can do that portion that might be, branchy on the CPU, and they can hand a pointer up to the GPU. It's a very, very powerful programming technique. I think one of the things that people actually get wrong a lot of the time about coherency is they think of it as purely a performance thing, and not a developer productivity thing. So these architectures at their simplest point go after the set of workloads that are on the CPUs today that scale as you build more GPUs. And at a slightly more complex point, they provide a demarcation line where you can take that workload and you can split the part that wants to be on the CPU, part wants to be on the GPU. Be very productive in how you split it. So it's kind of two worlds of what we're doing with that, if that answers the question.
Yeah. Let's talk a little bit. I cut you off there, Robbie. You want to?
I was just going to add. Well, yeah, I think he hit spot on. Like what can't the machine do now in this sense? Like it's been optimized so well for AI, ML, DL, right? So yes, you're taking full advantage of the GPU. You have this amazing CPU. Now you can take advantage of that as well. There's other, and so timing wise, we're getting close to NWC. NVIDIA is a great partner there. We have the AI RAN story going on, in our booth, and now it's like, well, now I can run these machines, at the edge, and they're doing more than I'm getting AI ML, sources close to the end user, and I'm running the normal services that I normally run on the server, but now I don't have to do two things. It's like a consolidation and optimization of getting, kind of the best of both worlds in a single box, right? Like you said, it's very efficient now that a developer doesn't have to go, oh, let me go switch over to this server to do this, and oh, the ML stuff, I gotta go over here. Now it's all in the same thing, right? So it's way more efficient in terms of being able to deliver what you need to. So
let's talk a little bit about Grace Hopper and Grace Blackwell, the super chips there. How do they handle different AI workloads, whether it's training or inference?
Yeah. So, I mean, the first thing I would say on that is earlier in the call we talked about the Grace super chip, and I want to kind of clarify our branding a little bit before I answer your question, which is that the Grace super chip was the CPU super chip that we were talking about earlier, heart and soul of a 2-socket compute platform on a module. There's other ways that we compose super chips. This will kind of segue into the answer to your question as well. We have different compositions of things like the Grace Hopper super chip, where you saw one-to-one coupling of the CPU and the GPU together, a certain amount of bandwidth between them. Moving into the Grace Blackwell super chip, you see a different module that has a different subscription rate of CPU to GPU. And that's the neat thing about looking at this at a system level, right? The super chip is all about system. And we can actually play around with the topologies, what we're doing to make different, different value propositions for people with different workload demands. And so a customer doing, co-located inference where they want to actually put the web server, the pre-processing, if they're looking at image data, they want to resize it, they want to scale it, something like that. I mean, there's all sorts of different ways you can architect this, but that customer might prefer, to co-locate some of their inferencing infrastructure right next to the GPU that's doing it. They might be compelled to go to something like a Grace Hopper super chip. You have something, like the Grace Blackwell super chip, and you'll see that the products we've announced today have a little bit of a different ratio of CPU to GPU power. Those might skew toward training scenarios. But on this particular call, I don't want to be as prescriptive as to what these things are for, because I actually think the message of accelerated compute is all about people being able to be more inventive in how they want to place their workloads and how they want to divide their workloads. And having that ARM CPU and a very capable CPU at a very low power, great memory bandwidth, co-located with your GPU infrastructure, you get to be a lot more creative. Hey, maybe I'm going to move some of these services that I was going to run somewhere else in the data center. Maybe those move right next to the GPU. Maybe the workloads that I was running on my CPU start to split, and we move some of those, to the GPU, because now we have coherent programming. So I'm not going to be on this call be really prescriptive about what topologies for what workload, because I actually think there's far more opportunity now than there was when the GPUs were, traditionally at the end of a PCI Express link, and you would copy data to them, you get it back. That put a much more, let's call it, definitive set of rules around what topology was for what workload than what we have.
So, Robbie, here's one for you. We've heard a lot about the structure of these devices, the utility, the workloads, the flexibility. Walk us through how you see ARM's architecture enabling the customization and power efficiency advantages in these solutions.
Sure. I mean, you're before warned, you're asking the software guy to talk hardware, but but hey, I've worked in hardware companies my entire life, so I live the fine line, right? No, I think it's funny because I think we've said ARM's architecture has always come from a heritage of an understanding of power and performance and the criticality of low power and high performance, right? Like we've been bred up from those roots, those ends, of where we started. I would say that one of the big advantages of ARM is really the approach that we do to licensing IP and our partner ecosystem, such that we're allowed to learn so much and feed that into the products that we provide, right? By working, with all these various hyperscaler partners, understanding their critical workloads, what they're trying to do, feeding that into our IP pipeline and creating the products that come out of the Neoverse and V-Series pipeline, we're able to at least do something that other people can't, because they're not opening up their IP to these partners, right? So we're getting the best of all these partners, and then we pull it together, and then we offer it to a new one, such as NVIDIA, and then they could tweak it to their own needs. Like, by the way, this is what we learned. These are the workloads that we've already done in our pre-silicon projections. We know about these workloads. Oh, but you're adding all these AI things. Awesome. Okay, so how do we work together there to make your product even better, based off of the data you feed us, right? And I think that is the real kicker, that the real it's the partnership, the ecosystem. Together we build these great products, right? And you're benefiting from it's like a kind of like the whole open source approach, but obviously it's not open source, but it's like you're benefiting, it's crowdsourcing the best. And then we deliver that to you to customize to your own unique needs, right? It's kind of the best of both worlds there. And so I think that's what ARM really brings, right? And again, based off of our heritage of power and performance, that you can't just outright run without any concern over power. It's especially now that these data centers get larger and larger, power consumption is important. And so, as someone who has to sell it, NVIDIA is like, look, we definitely need to deliver performance, but we are conscientious about the power that it takes, right? And so, and the cooling and everything else. So I think that's what really ARM brings to that, is that flexibility and crowdsourcing.
So, Ian, how did the software guy do on that one?
I was going to ask, I really like a couple aspects of Robbie's answer that they stick with me, and part of that, you guys can edit this out if you want, nudge him on this particular topic. And I actually don't inherently believe that in an age where the instruction set architecture has so many abstractions on top of it, I don't believe that there's anything inherently power efficient about ARM as like an ISA. And that's a common misconception. People come up and they say, ARM is inherently more power efficient. And it's not, and that's not a knock. That's what I love about Robbie's answer, is because what ARM does do is it frees us to put forth products with different value props, particularly different value props around performance per watt. It frees us to really look at our system design and figure out where to get all the power back and put something forth in the market that is differentiated in those respects without having to worry, how the heck are we going to boot this thing? Where am I going to get the driver for the NIC? How is someone going to run Python on it? So I think you did great.
Yeah, I mean, let's be clear. There's other architectures out there that also claim power efficiency, but their software ecosystem is not as robust. It's the wild, wild west of which we've come from, and that's ultimately where things start to break down, and that where the work that ARM's done and NVIDIA's done in the ecosystem, all this work on the software side pays off, right, for everybody.
Right. Okay, so Robbie, a software question for you. So let's pretend I'm a developer and I'm for some amazing reason new to this whole world of NVIDIA and AI and developing on NVIDIA devices and ARM devices. Where do I start? What software tools and resources are available for me to get started?
What's not available for you, right? And I mean, to be honest, and really, no joking aside, right? Like in terms of, especially with NVIDIA, right, and the CUDA ecosystem, all the work they've done, it's a no-brainer in terms of where do you go, for example, right? I mean, yes, there's a tons of open source tools as well. PyTorch is, I think Ian mentioned before. I mean, it's more of what doesn't work, and it's a slim amount of things, right? And if it doesn't, it's probably on the way to being optimized and ported, right, and so forth, right? But yeah, I mean, I think, yes, access to the hardware has gotten a lot easier, and that that's where the digits and obviously clouds and access that's probably the bigger hurdle. I think there's been so much work, kind of done by our partners in this space, like NVIDIA, Amazon. They're great open source, contributors for ARM, but and because it now all works across the board, you're not, again, I don't have to have PyTorch for NVIDIA and PyTorch for, Cobalt 100 on Azure and PyTorch for Amazon. It's all the same binary, in terms of working. I think now the question really is, please find the stuff that doesn't work, and we want to know about it, but you shouldn't really stumble. Outside of some of the newer tools that are being developed, but now they are being developed in a multi-architectural mindset of, now it's not just one architecture I need to support when I develop these tools. I need to really, and now there's the CI/CD and GitHub runners in place for all these folks to exist, right?
So let's assume I'm hearing a lot about all the cool kids are developing on ARM-based solutions, but I don't right now. How do I migrate there? What's your perspective on porting my applications over? How does that work?
It depends on what you're porting, like, in a sense of, in some cases, using a cloud instance is fine because you're at such a high level, you don't really need to know a lot about the hardware underneath, or you don't need to do a lot of prescriptive things. Other cases, you may need, an NVIDIA server or the scaled down version of, digits, which is pretty awesome, by the way. But I think it depends on where you're a developer. If you're an OS developer, if you're a low-level library developer, you're going to want bare metal hardware. Then you have options for an Ampere server. If you got big bucks, you can buy an NVIDIA-grade server, or now the Digits is out there, which is like
I
the
think you'd be
awesome.
pleasantly surprised at our pricing.
Oh, well, yeah, but I've bought the servers, but the Digits is awesome, right? Like, I'm really geared up for that as a, that's like the Raspberry Pi of Grace for in a way, right? That's pretty, as a developer. And then obviously there's laptops coming on the space, and if those can, that's another big push. So it's all about access to hardware. But I think as a developer, it's really about, where are you targeting? Do you need, can you just run off a cloud instance? Then go do that. That's probably the easiest thing financially for you. But again, a lot of people need to develop, in a corner with no internet on a plane. Then you need a device. There's, laptops coming on there that are ARM based. And again, the Digits platform, which is, I love that type of hacky stuff like Jets and Nanos and all that stuff. So I'm all about. But yeah, I think it's really, I think they're, ARM has been running this Works on ARM program. You can you can look that up, and there's like a lot of different options of partners and how to get access to their hardware either remotely or in your hands. But it was a problem, I'd say 3-4 years ago, but it's gotten a lot easier in terms of getting access to the hardware to do the development you need.
So that FUD that you hear out there that porting to ARM is hard is just that?
That's a tricky question. Porting software to any architecture is easy. Having it run well is the hard part because, and I've done this. I've ported different Indian, I've done this, right? And you'd recompile port, pretty straightforward unless you have some weird, assembly language in there, intrinsics. But it's not that easy. You still have to then look at that software and, if you want to perform well, really understand what the architecture you're running on. And that takes a little nuance. There's a lot of material out there that ARM provides, learn.arm.com. NVIDIA provides a lot of material as well to kind of understand how to tune your applications. But that's generally what you're going to have to do anyway, even on x86 platforms when you move from one to another, to really get the best performance out of it. But porting, recompile, go, right? But go ahead, Ian.
Right.
Well, that was exactly what I was going to say. That is, almost like, Robbie's giving you the point of view of someone who's actually sitting there, porting the stuff. And for most of the people who think about this whole porting to ARM is hard. They're generally like enterprise customers or, academic customers, things like that. And if you go look at their stack, all the key areas of growth in their infrastructure are all like free open source software, Linux, Apache Spark, Hadoop, it's all FOSS stuff that exists, and actually someone has done that hard work that Robbie's talked about, sat there, on their laptop playing golf, with all the code generation tools. And for those tools, it really is like just about the same level of tuning as you do on an x86 platform. If you're running on I'm not picking on AMD here. If you're running on like an AMD platform, you have to worry about subNUMA islands, right? You get like 8 cores per chiplet. And you have to worry about subNUMA islands in a lot of configuration cases. You have to tune things. Oh, where in the chip do my containers live? That kind of stuff is actually in some ways harder for the end user to deal with, because the end user is the one who's making those are deployment time concerns, deployment time tuning concerns. And most of the stuff that our customers deal with in terms of actually having good optimized binaries on ARM, that's there today. For all of the kind of free open source software ecosystem, ISVs more and more every quarter, pretty much every ISV we talk to has a decent ARM build in house, whether they're talking about it yet or not. And that's tremendous to see. And the reason for that is high performance ARM products entering the market, in the last couple of years.
Yeah. I think one thing I would add is also, like, again, especially at the enterprise level, you you do run into legacy apps where maybe the developer left and they can't,
That's true, but I have a I have a certain opinion. I'll go back to, you said something like, you got big bucks, you can buy Grace. Grace is actually very inexpensive. And the reason it's inexpensive is because for the performance it has on analytics workloads, on data warehousing type workloads, I promise you, it's the least expensive thing in the long run you can buy.
Absolutely.
And those types of workloads are the engine of all the data center growth. So just like today, you go to a large customer and they have a mainframe somewhere and it's running their line of business transactions and it's producing a data set. And all of the research and analysis and insights that they're building from that enterprise data, those are growing in places like free and open source kind of ecosystems or accelerated ecosystems alongside the data. At the end of the day, that thing runs a batch job, produces a bunch of data, and then the heavy compute begins.
The real work happens. Right.
And all of that is ARM native today. It's growing. A lot of it is accelerated. Even more of it's being accelerated. And it's really the insights on the data sets that are being produced by those legacy applications that I believe are the real growth area.
So let's look ahead, because we're going to be bumping up on time here pretty soon. Where do you guys see the biggest opportunities for innovation in this partnership?
I think just continuing to offer a really solid foundation that frees our cycles to focus on our systems, on our hardware architecture, and not have to and have something that the rest of the world can use. I mean, that's
I would agree. I think it's, as unsexy as it sounds, like, let us do the commodity part for NVIDIA, which is the CPU. It's great, but let them focus, I think the more we can focus on the parts that we do best, the better it is for both sides in a sense, right? And as accelerated computing gets way more, spread, used, and as we approach, the AGI and the Skynet, world, accelerated computing and the fact that we're allowing, partner like NVIDIA to innovate and iterate on the parts that they care about most, but have a reliable core that they know is going to be there, and that they can also, push towards their needs still, right? I think it's going to be, it's just kind of keep doing what's working, right? In that sense.
So what should developers and organizations be thinking about as they plan their technology roadmaps? I mean, I'd like to oversimplify it and say it's up and to the right, but that's probably simplifying it. What do you guys think?
That's a loaded. Do developers plan the technology roadmaps really, or is it like the total?
How about decision makers?
I wish developer. I'm sure. I know some developers who wish they did. Right? Yeah. I think plan for a multi-architecture, first-class citizen environment where, I'm not going to be naive and think x86 is going away, right? But you have to play. I think as ARM becomes more prevalent and the accelerated workloads, you need to really architect your solutions, your data centers, everything you do around a true multi-architectural world. What does that mean? CI/CD, maintenance, everything has to be thought of. And now that I'm really living in, and a lot of, and to be fair, let's say, x86 has dominated for so long in the data center. A lot of folks have never had to do this unless familiar with maybe an IBM Power or a mainframe. But these are niche areas like finance and things. So you've lived that. But I think that is, we're dealing with partners now as they adopt ARM internally. They have their own ARM products. They're like, this isn't a lift and shift. This is an expansion. And so now we're having to reconsider all of the way we approach things. And I think that's just something, we just got to really start thinking about that. You're living in a world where, you're going to have to be aware of the underlying architecture to an extent because you're going to be placing workloads and so forth.
But it's also not as daunting as it sounds, because
No, that's true. I mean, it's not recompile and everything else. You're right. It's just be aware of it. Yeah.
You start where it makes sense. Oh, I'm doing all this accelerated compute. I'm doing all this analytics. I have all this, I have a bunch of products that I'm using for that. Let's buy some ARM compute servers. Let's buy some ARM accelerated servers, and maybe that partition, that can be an ARM only, partition. I mean, you got a huge handful of vendors. You got NVIDIA now selling the CPU products. If you need more CPUs, buy more CPUs, to go alongside your GPUs, and start to think of where you can kind of group these birds of a feather together, because you don't have to, it doesn't, supporting multiple architectures in your data center doesn't mean that you're doing like VDI, on
Right.
ARM today, right?
Right. And every application has to work across every no, you could be very selective about it for sure. Yeah. Targeted.
And I think for what's a recent development is some of those pillars can be easily, ARM only or even NVIDIA only pillars at this point. Now that we have a data center class CPU offering. Hey, we're only maintaining this particular distro, this particular set of libraries, this particular binaries. That's just going to be Grace CPU, Grace GPU, and the task becomes much less daunting when you don't have, multi-architecture support in every swim lane.
Well, you gentlemen have been incredibly generous with your time. Thank you so much. We look forward to seeing you at GTC, and best of luck this year.
Thank you.
Awesome.
Yeah. Cheers.